The Earth's atmosphere behaves like an enormous, invisible rubber band, constantly stretching and snapping. This elastic behavior drives incredible shifts, from sudden Arctic blasts to prolonged, suffocating heat waves. Understanding this atmospheric elasticity unlocks the secrets behind our planet's most dramatic weather events. It explains why conditions can drastically change overnight, impacting millions across vast regions. Weather isn't merely random, but an intricate dance of colossal air masses and energy transfers. Our atmosphere is a dynamic fluid, always seeking balance amidst constant solar heating and planetary rotation. These powerful forces generate persistent, high-altitude air currents, fundamentally shaping global climate patterns. One critical player is the powerful jet stream, a ribbon of fast-moving air circling the Earth. Imagine this jet stream as a giant, flexible boundary, separating vastly different air temperatures and pressures. It acts as a massive atmospheric conveyor belt, transporting weather systems across continents at incredible speeds. Without this crucial atmospheric river, localized weather would become far more stagnant and unpredictable. Its position and intensity directly dictate where storms form and where stable conditions prevail for weeks. This invisible highway profoundly influences daily life, from agriculture schedules to international flight paths. Farmers rely on its stability, while aviators meticulously track its ever-changing, powerful, high-altitude flow. The jet stream's elastic, rubber band-like properties are central to understanding these complex atmospheric dynamics. This powerful river of air forms where cold polar air masses meet warmer tropical air masses. The sharp temperature contrast creates significant pressure differences, accelerating air into a swift, narrow current. Earth's rotation, known as the Coriolis effect, then deflects this moving air, solidifying its eastward path. But this atmospheric rubber band doesn't always maintain a straight, predictable path across the globe. Instead, it constantly meanders, developing enormous waves that stretch northwards into Arctic regions and southwards into tropics. These colossal atmospheric waves are called Rossby waves, acting like ripples on a vast ocean of air. The jet stream's stretching phase occurs when these Rossby waves become particularly amplified and elongated. This deep undulation pulls cold air far south and warm air far north, creating extreme temperature anomalies. Yet, the most dramatic atmospheric events emerge from an even more extreme elastic process. Sometimes, these deep meanders become so pronounced they can effectively pinch off a section of the flow. This pinching creates a phenomenon known as atmospheric blocking, forming a stable, high-pressure system. Imagine a rubber band stretched to its limit, then tied into a knot. This knot is the block. This stationary block can persist for days, even weeks, diverting the main jet stream around it. The snapping effect happens when the stored energy within these stretched systems suddenly reorganizes. A blocked pattern might abruptly collapse, allowing the jet stream to quickly return to its more typical flow. Wait until you hear what comes next regarding the incredible speed of these atmospheric adjustments. This sudden reorganization can bring rapid shifts, ending prolonged droughts or triggering intense storm outbreaks. The speed of this snapback depends on the magnitude of the pressure gradients and temperature differences involved. Another fascinating example of this elasticity is the quasi-biennial oscillation in the tropical stratosphere. This oscillation involves alternating easterly and westerly winds that repeat approximately every 28 months. It demonstrates how stratospheric rubber bands can influence tropical cyclone activity and winter weather patterns. And the atmosphere holds even more surprising long-term elastic secrets you might not expect. These global oscillations, like the Pacific Decadal Oscillation, also exhibit profound long-term elastic behaviors. They shift vast ocean temperatures, which in turn stretch and contract atmospheric pressure zones for decades. Every stretching, every snap, every oscillation profoundly impacts the weather systems we experience daily. The real-world consequences of this atmospheric elasticity are truly far-reaching and impactful for everyone. A stubbornly stretched jet stream can cause devastating, record-breaking heat waves to bake continents for weeks. Conversely, a deep southward dip can usher in brutal, prolonged Arctic freezes, paralyzing entire regions. Atmospheric blocking, the tied knot in our rubber band, often leads to persistent droughts or relentless flooding. Imagine a city trapped under a stagnant high-pressure system, enduring days of choking smog and scorching temperatures, or an agricultural region suffering catastrophic crop losses from an unexpected, unyielding cold snap. Understanding these elastic patterns allows meteorologists to improve long-range weather forecasting capabilities significantly. Better predictions enable communities to prepare for extreme events, saving lives and protecting valuable infrastructure. This knowledge empowers farmers to make informed decisions about planting and harvesting, optimizing their yields. Shipping companies can reroute vessels, avoiding dangerous storm systems generated by these powerful atmospheric shifts. Aviation benefits immensely, as pilots adjust flight paths to leverage favorable winds or avoid turbulent zones. The more we comprehend the atmosphere's elastic nature, the better we can adapt to its inevitable changes. These invisible forces shape our world, from local rain showers to continental weather extremes. Humanity's resilience depends on continually deciphering these complex, dynamic atmospheric behaviors. Ultimately, the Earth's weather patterns are governed by an intricate, ever-changing atmospheric rubber band. Its stretching, snapping, and oscillating profoundly dictate the warmth, cold, and wetness we experience. This constant atmospheric dance ensures our planet remains dynamic and never truly static. Recognizing this elasticity helps us appreciate the delicate balance of our global environment. Understanding this elasticity is key to predicting and adapting to our planet's future climate. If you found this fascinating, subscribe for more incredible stories and leave your thoughts in the comments.